Hello everyone. In this video, we discuss how to implement linear regression in scikit-learn or sklearn, which is one of the most popular machine learning libraries in Python. And also we will show you how to use built-in scikit-learn methods to evaluate the performance and accuracy of regression models. To provide a quick summary of the previous discussion, remember that in regression models, and in particular linear regression, we have input features, and we show this using vector x, which can be a d-dimensional vector. And this vector goes through a linear transformation by finding the inner product or dot product between theta and x. This gives us predicted output. And then we compare this with the true output using the mean squared error. And then we set up an optimization problem where we find the gradient of the loss function with respect to the parameters. So last time we started with the univariate case where xn is a scalar, and we showed you how to find the gradient, which has this form in terms of the summation between residuals and summation between residuals and the input features. We showed how to find a compact representation of the gradient using data matrix X, which is of size n by 2, in this case, because we only have one feature. And then we have a parameter or weight vector theta, where theta 0 is the intercept, and theta 1 is the slope of the line for our linear regression model, right? So here is the equation. We have theta 0 plus theta 1x. So the goal is to find the best values of theta 0 and theta 1 such that we minimize this loss function. And we showed that we can solve this problem using the least square method, which is already built in and implemented in NumPy's linear algebra or linalg module. And then we showed you how to use or extend this discussion to the case where you have a vector input feature vector. So in this case, you can see that this xn is d-dimensional. Therefore, in this most general form that we see, we have theta 0 as the intercept, and theta 1 are the theta 1, theta 2 to theta d are the slopes or coefficients. Mathematically, we can assume that the first feature is always 1. So in this case, instead of a d-dimensional vector, we actually get a d plus 1 dimensional vector, where the first element is always assumed to be 1. And therefore, we can write this prediction that we have as the dot product between theta and x, where theta has d plus 1 elements. And in this case, our loss function also can be written as the Euclidean norm square of y minus x theta. X theta is the vector of predicted values, and y is the true or target vector that we have here that we use for training our model. And in this most general form, x is our input data matrix, is a two-dimensional array. We have n rows, and also the number of columns is equal to the number of features plus 1 if we assume that vector of all ones. And the goal of linear regression really is to find this parameter or weight vector, which we have d plus 1 element. So in order to implement linear regression in scikit-learn, the very first thing that you want to do is to import linear regression. A linear regression is part of scikit-learn's linear model module. So the way this works, inside scikit-learn, there's a module called linear underscore model. This is for the cases that you can use that dot product or inner product representation. And there are other machine learning methods too, but since here we are focusing on linear regression, that's what we import. Remember, this is a class. So first you have to instantiate it. You can do this by providing these parentheses without extra input arguments if you want to use the default values. And once you create this object, which we call it here model, or you can call it anything else, you can use a method called .fit, which means that you want to now find that parameter vector theta. So that's what this does without going into details. And then once you have found this vector theta, we can use that to make predictions. We said that this is a new feature data matrix X or X test times theta, which we can do this using model.predict. In this case, obviously, you don't really have to use model.predict since the prediction part is relatively simple, but it is nice to know in most cases when you're using with scikit-learn how you can do model fitting and how you can do predictions. And remember, when you want to make predictions, you do not provide the output labels or the true outputs here because the goal is to predict them. Later, when we go to the evaluation part, that's when you want to provide these predictions and the true outputs to be able to find them or find the accuracy of the model. And in terms of once you train this linear regression model, there are two attributes that are very important, and you can access them through .coef and .intercept. .coef includes the coefficients or weights for the linear equation. So these are all like theta 1, theta 2 to theta d. And intercept is always theta 0. So for purposes of scikit-learn's implementation, they try to separate these. So this intercept, which is theta 0, is not included inside this coef. So coef only includes theta 1 to theta d, and this is the one that is intercept. And in order to get more information about linear regression implementation, my suggestion is always to look at the documentation page, right? So here you can see all the input arguments you can provide when you want to instantiate linear regression class. The most important thing is the fit intercept, whether you want to consider that theta 0 term or not. And in this case, we set this equal to true, meaning that yes, we want to have this. You can see that then there are attributes like coef, as I said, for the coefficients that we have in our linear regression, and also the intercept, which includes the y-intercept that we have, the theta 0. There are also a few other attributes too, where we don't use them very much. For example, like the rank of matrix X. If you have had linear algebra, this is something that is probably familiar to you, and this is very important if we really want to talk about the stability of the solution, and if you're worried that we may have features that they are linearly correlated or dependent. And then the other thing that is very important is these methods that you can use. So as we mentioned, we can use .fit to find the parameter vector theta. X is the data matrix. It must be a two-dimensional array of size number of samples, which we use uppercase N, and number of features, which is in this case uppercase D. Remember, with linear regression, when you are using scikit-learn's implementation, you do not need to add the vector of all ones as the first column. So linear regression by itself will take care of this. This is exactly the idea behind that fit intercept that we had before, that if we set that to true, then it means that linear regression implementation will automatically add that column vector of all ones, and you do not need to do it yourself. So that's the nice thing about using these libraries. And Y is something of size, usually number of samples, is a one-dimensional array which contains the target or output values. In this case, you can also work with multiple targets. So far, we only consider the case we have only one target output, but in reality, you may have like two or three more. So this implementation of linear regression also can handle multi-output scenarios. And that's something that we will discuss later, but the math here is very much the same in a sense that you can think of these as multiple linear regression problems that they are independent of each other. And also you can see some other methods like predict, which we really use a lot, but there's also some other ones like a score, etc., that you can use to simplify the process of evaluating linear regression models. Therefore, my suggestion is for any machine learning method in this course to go through the documentation page, read this description. Also look at the examples that are provided. These examples are really nice to understand how things work in scikit-learn, and that's one of the best ways of getting quick information about these machine learning methods in scikit-learn. With that said, let's go back now to what we have for this Jupyter notebook that we have here. So in this case, one thing that we also want to do for this GDP data that we discussed previously, which we want to predict life satisfaction, we can use some pre-processing that we discussed in the previous module. In particular, we use min-max scalar, so this is a good practice. We instantiate our preprocessor. We use fit.transform. So this makes sure all the features are between 0 and 1 in this case. And therefore, the nice thing is that therefore like theta 0 and theta 1, they're more in the same scale, right? Instead of before where theta 1 had to be really, really small because the values of these features were really, really large in the order of 10,000s. And after this pre-processing, we instantiate the linear regression class. We create an object called reg or reg. So as you can see, this name is arbitrary. You can use any variable name you want. And we use .fit, and we fit this to the pre-processed data. And now we look at the attributes, intercept, and coef. So here you can see that we got this error message that the name linear regression is not defined. And this is because we did not import this. So something you want to do, this is always a good practice. We can say from sklearn dot linear model import linear regression. So if we do this, now you can see that we don't get any error messages. That's what a good thing that we just saw that because we already imported the pre-processing function. We need min-max scalar, but we also need to do that with linear regression as well. And in this case, you can see that the intercept is this 5.54, and this is our coefficient that we have. So this is technically theta 0, and this is theta 1. And in order to plot the prediction model here, we can provide this a scatter plot of our training data that we use, this x min max with the corresponding outputs. Also, we need to find, since we want to draw a line, 2 points on this line. But something that is very important here is that our x test needs to be transformed using the same exact method we did our previous data set. Therefore, we have to make sure that we transform these using this min-max object. And now we can draw these by providing the inputs and looking at the outputs of our model, which can be found using .predict. And then we can also put the x and y labels. So here on the x-axis, we have GDP. In this case, we have scaled this. So the GDP values are from 0 to 1, from smallest to largest. And then on the y-axis, we have this life satisfaction score. And you can see that here we have a model that relatively well explains this data set that we have. So obviously, linear regression is not 100% accurate in this case, just visually looking at this, but you can see that overall does capture the overall trend. And in order to make this more formal, like how good or accurate this model is, we need to look at evaluation metrics. And the quality of regression model in general, so this part of this module applies to any regression model. Later, we will focus on more complex models, and these evaluation metrics are applicable to those cases too. You can click on this link here, and you can see that we have a whole list of like methods for finding like performance or accuracy of regression models. And you can see here that it explains to you the scoring parameter and specifically the names of metrics for classification models that we will cover in a future video. And also there should be here the regression model. So here's what we really want to look at. Methods such as explain variance, negative mean absolute error, R2 score. So the goal here is that in the rest of this video, we're going to go through a few of these things that are very popular and widely used, but you can see that we have 10 or so evaluation metrics that you can use, and obviously there are differences between them. And the goal is to kind of go through them right now. Okay, so the very first metric that we want to talk about is mean squared error, or MSE. So in order to find this, we need a vector of true outputs or targets, which is this y, and y hat is the vector of all predictions. And since we have, let's say in this case, n test data points that we use for testing a stage of this machine learning pipeline, this means that now we have yn and y hat n, where this subscript n goes from 1 to n test. And MS is very familiar because that's exactly what we use for training our regression model. And the way that you can find this is by 1 over the number of test data points and then the sum of all these residuals raised to the power of 2. So obviously, if our model is perfect, meaning that all y_n's are exactly equal to y hat n's, then the MSE score would be exactly 0. And obviously, it's always non-negative because of this power of 2. And therefore, the goal is that closer to 0 is better. One thing that we need to take into consideration when you work with mean squared error is that the value you get after calculating MSE is a squared unit of output, which can be a problem. Let's say the output is like you want to, for example, predict the MPG of a car. And in this case, if you look at MSE, the unit is not anymore MPG, it's more like MPG squared, which may not really make sense. Therefore, in this case, one thing that we can do is to look at this new metric known as RMSE, or root mean squared error, which is very much the same thing, except that now we take the square root of this, which is very much like similar ideas to like when in the statistic we look at variance versus a standard deviation, right? So you take the square root of variance, you get standard deviation. And here is the same thing. We have mean squared error, which is in the squared unit of output. And also the other issue with mean squared error is that it's very sensitive to a few really like maybe like, bad cases where our predicted values are very far from true values, which we can call them outliers. In order to show you how you can use these metrics in scikit-learn, so in scikit-learn, there is another module that is called metrics, where you can find these evaluation metrics. And in this case, we import mean squared error and root mean squared error. So MSE and RMSE. And just to make this very simple to understand, let's say you have a vector of true outputs or targets and predicted ones. And we find both mean squared error and root mean squared error, which in both cases you have to provide y true and y pred. And as you expect, so here MSE is 0.25, which is 1 over 4, and root mean squared error is 1 over square root of 4, which is 1 over 2, which is 0.5. So this one is very simple to understand. It's one of the things that we have used a lot. There's also something called R2 score, or the coefficient of determination. The formula for this is 1 minus these residuals that we have in the numerator, that they're raised to the power of 2, and we add them all together. And in the denominator, we have a little bit like a different formula. We have the true outputs minus the average or sample mean. So y bar is the average of all the y_n's. So what does this mean? So the numerator here is very familiar. Is this residual sum of squares that we have been sort of like working with that before, which measures the variability that is left unexplained. So this means that After we subtract these predicted values from the true values, this is how much we have left. And you raise this to the power of 2. So obviously, if again we have a perfect model, all y(n)s are equal to y hat n's, which means that we get 0 in the numerator, which means that we get 1 minus 0, which is 1. So therefore, when you're working with r squared or coefficient of determination, the best possible score is 1, regardless of the range or scale of your outputs. And this is really nice in the sense that regardless of what the outputs are in range of, like, let's say from 1 to 10 or 1 to 10,000, the best possible score for r squared is 1. However, the interesting thing is what we have in the denominator. So what denominator is really saying is that, well, in many cases, a machine learning model can just predict the average output of labels or the targets as the predicted value for any new test data point. So in that sense, let's say if we have a very boring machine learning model where these y hat n's, they're always equal to the average, to this y bar. In that case, the numerator and denominator are equal, which means that they cancel, and we get 1 minus 1, which is 0. So an r squared of 0 in a regression model means that the model predictions are no better than simply predicting the mean of the target value or target variable for all data points. So therefore, in this case, 0 is a good way of saying that, well, we want to be closer to 1, and hopefully as far as possible from 0. But if we are close to 0, means that our machine learning model or our regression model is really boring because we are very much just predicting the same output for any new test data point, and we are not really learning anything. On the other hand, something that is very important about this r squared, because we use this power of 2 here, even though we are not technically raising here to the power of 2 in the complete form. Of course, we have some like residuals here raised to the power of 2, but not this whole thing is not raised to the power of 2. And we may think that, well, this should be positive, and this is not true. So you can actually design a machine learning model where these y hat n's are such poor predicted values or predictions, such that this ratio here that we have, 1 minus this ratio, can be greater than 1, and therefore r squared can be negative. Usually, if r squared is negative, you know that there is something wrong with the setup, meaning that either you really have to think about, like, better ways of pre-processing your data, or maybe you have to use like a completely different regression model. So it doesn't happen too often, but it is something that is possible to happen, that r squared can be negative according to this formula that we have. And hopefully, again, the goal is we are as close as possible to 1. And here you can see that what we have done to just show you this, I created like these sort of like inputs X. These are the actual outputs Y. And let's say we have a machine learning model that, predicts this output for test data points. And in this case, if we plug in into this formula that we have for r squared, you can see you can get a negative value. So the goal here is just to show you that, yeah, it is possible to get r scored less than 0, which is kind of like counterintuitive, but given the formula that we have, it is possible. And here we can see that we have the implementation of the residual sum of squares, and then what we have in the denominator. And by the way, the one that we have in the denominator here, it is very much related to the variance of these y(n)s, right? Because if I divide this by 1 over the number of test data points, then we get the sample variance, which is these random variables yn minus their sample mean, and then divided by the total number of data points. So that's why we can think of this denominator technically as the variance. And this takes us to the last metric that we want to discuss here, although there were more metrics for regression problems, and that is why it's known as explain variance. So explain variance is related to the coefficient of determination, but a little bit different. So in the sense that the formula is 1 minus variance of y minus y hat over variance of y. So variance of y, as we said, is what we have technically in coefficient of determination, or R to a score 2, because in that case we had that yn minus y bar squared. That's part of the definition of the variance. However, here in the numerator we also have variance of y minus y hat. The idea is that, again, if y is exactly equal to y hat, meaning that all predicted values are exactly equal to the true values for the output, then this is a vector of all zeros and the variance is 0. And therefore we get 1 minus 0, which is 1. So scores closer to 1 are better and lower values are worse. And we can actually show that when the residuals, so the residuals are yn minus y hat n, if we go back to this formula. So these are residuals. So if residuals have 0 mean, then the explained variance score and R2 score are identical. So they're not always equal, but if we have residuals that they have 0 mean, then the explained variance score and the R2 score are identical, which is very nice, this very nice mathematical connection between them. So just to recap what we covered here, we can use scikit-learn to implement and train linear regression by instantiating that and creating this object using .fit, .predict. Once you use .predict, you have now your predicted values, and this will give you the y hat ends. So in this case, you can now use scikit-learn metrics, including mean squared error, R squared, or coefficient of determination, and explain variance, and you find different ways of quantifying accuracy of your model. So you can see that the way MSE works is different than, for example, explain variance, in the sense that lower values for MSE are better, whereas for explain variance, values closer to 1 are better.